Hello and welcome. In this chapter, chapter 25, we introduce the concept of the electric potential, and we also review energy and introduce electric potential energy. Electric potential is probably one of the more confusing topics in this entire course, but it will ultimately lead us to the concept of voltage, which is seen everywhere in electronics. Tiny voltages that we use to power our transistors, or the voltages in battery for our consumer electronics. The concept of the voltage comes from this confusing electric potential. So I want to get straight into it and talk about, first review what energy is, okay? So let me hop on the slides here quick. Okay. All right, so this is the first kind of chapter review of energy. The idea is that the electric force is a conservative force, just like gravity. And so the concept of potential energy is defined for a conservative force, right? There's several different implications or equivalent conditions for a force to be conservative. The one that we use is the fact that the work done by that force can be expressed as the change in a potential function. That is, the work done between 2 points, no matter what path you take between those 2 points, is always just the difference between a number at those 2 points. So it doesn't matter what the path is you take to get from A to B, it's just a number at A and a number at B will give you the work. So that's helpful. You don't need to calculate the work with a complicated integral. You can just take the number at the beginning, number at the end, and their difference. And as far as work, just a reminder of the signs of work, because the signs of work are important. The sign of work is positive if the force is in the direction of the particle's displacement. It's zero if it's perpendicular, right? So lifting an object, when you lift an object up, when you're carrying that object, right, gravity's not doing any work on it. And similarly, in circular motion, when you have moons and asteroids and planets orbiting other objects in circular orbit, those, like the sun, doesn't do any work on the Earth, and so on. Work can be negative when the force is applied opposite displacement. And you remember from the work kinetic energy theorem that in the first case of the work being positive, that means the speed increases. If the work is negative, the speed decreases. If the work is zero, the speed holds steady, right? That's why a particle in circular orbit never changes its speed. And so we can go back to the concept of gravity to remind ourselves what potential energy is. So when an object falls, it has a decrease in potential energy from positive work done. So that negative sign at the beginning there, right here, in the middle here, that negative sign is important, because if the work is positive, that means the potential energy is negative, but that means the kinetic energy is positive. You might even think on the left side of the work in that equation, that work is also set equal to positive kinetic energy. That's what the work kinetic energy theorem is. And so we want to transfer these ideas over to electrostatics. And the easiest way to do that is to consider what's happening inside of a parallel plate capacitor. In a parallel plate capacitor, the electric field is uniform. And so this is like a constant gravity situation for a charged particle, right? So you take a positive charge and you release it from rest. The electric field is going to do positive work on it. And so since what's the magnitude of that force? It's just Q times E, little q being the charge, positive test charge. And what is S? S is the displacement of the charge. And so the work done, so as you release the particle from rest, the work done is positive. It's positive Q times magnitude of the field, E, times magnitude of displacement, S. But from the very beginning, you knew that this work has to be, since the electric field is a conservative force, this work has to be expressed as some change in potential energy. And so we define the potential energy for a point charge to be Q times E times S, where S is measured specifically in this equation or in this situation of parallel plate capacitor, where it's defined as being from the origin, being from the where the origin is the negative charge and the position is increasing to the positive charge. And right, just like gravity, you can have the zero of the potential energy wherever you like, and you can actually graph what that is, that positive charge. What's interesting about gravity, though, and these are the things I'm just kind of going through it. So if the positive charge is pushed, if you apply a force, well, let's say if it starts moving towards a positive, that means its potential energy increases and its kinetic energy goes down. So this is basically like throwing a ball up into the air if the picture of the ground is switched, rotated 90 degrees clockwise, right? This is all expected for like a ball tossed in the air. What happens, and that's what's different, is that inside the parallel plate capacitor, the same parallel plate capacitor, a negative charge has negative potential energy because of its minus sign. And so this is like almost anti-gravity. If you imagine like throwing up a ball, right? If you imagine releasing a ball from rest, and if you were to imagine that it instantly just like accelerates upward and hits the ceiling and just stays there on the ceiling, that would be like what the negative charges is doing in the electric field, right? Because in the room that you're in, there's a gravitational field that points straight down and it's constant, magnitude 9.8 meters per second. Same thing here. If there's an electric field pointing to the left, positive charge is going to fall to the left, but negative charge will fall to the right against the field. And so they have electric negative charges in parallel plate capacitors have a potential energy equal to minus QES. And so here we see the graphs of the potential energy diagrams for the positive charge. What about for 2-point charges? For 2-point charges, the situation is a little bit different because the force is variable. Since the force is variable, we're going to have to integrate to find the potential energy, right? The general definition for force, for potential energy in terms of force, is the integral. It's technically the minus integral of the force over the, integrated over the position variable. And so you have the electric force between two charges, being K, Q1, Q2, or big Q, little q over R squared. You have to integrate that to get K, big Q, little q over R, and then take the difference between the 2 points. So the formula for electric potential energy between 2-point charges is variable, and because the it's a function of R. Now it's positive when you look at this formula for electric potential energy, the Q's do not have absolute values. And so if they're both positive, if the electric field, or sorry, if the point charges are both positive, then they will share a positive potential energy. If they're both negative, they'll also share a positive potential energy. But if they are oppositely signed, they'll have a negative potential energy. And the key is that if there's a negative potential energy, it means they're bound together. Kind of a negative potential energy between two objects means that they're kind of stuck together, they're bound together. Atoms that form molecules are in a state of negative potential energy because they're bound together. You need to do work to separate them. You need to do physical work to break those bonds, you know, usually by putting them in water or some sort of solution. So positive potential energy between two particles means a scattering situation. Okay, so no matter what positions they're at, if it's a positive potential energy, what you see here is that they'll move, their distance will increase as they move further away from one another. Well, duh. Their distance will increase as their potential energy decreases. So if you imagine two positive point charges separated by some distance, you release them from rest, what's going to happen? They're both going to shoot away from each other, and their shared potential energy will decrease, right? The 2-point charges always share a potential energy. I mean, it turns out that the Earth and the rock that you drop on the Earth both share the potential energy, but since the Earth was so much more massive than the rock, we never considered the possible motion of the Earth. Now we're dealing with with point charges that can both move around one another very easily. And then here we see the negative potential energy of a pair of oppositely charged particles. Right? So this case of positive potential energy is for two like charges. This negative potential energy is for two oppositely charged particles. So released from rest, they're going to crash towards one another, or if you can fix it in some way, they'll orbit around each other in some way. If we have more than 2-point charges, then we add their potential energies pairwise. It's always the case that more than 2 charges have potential energy pairwise, but you have to add them. So if you have, for instance, 3 charges, the total potential energy of that system would be the potential energy between 1 and 2, plus the potential energy between 1 and 3, plus the potential energy between 2 and 3. And you can imagine that it increases from there if you have 4 or more charges, that you have to add the potential energies of each one of them, not repeat them, but add each pair of indices together. You never take the potential energy of a particle with itself, because that doesn't make any sense. That would violate Newton's first law, saying that forces have to be external agents acting on a massive object. What about the potential energy of a dipole? This is where we return to the concept of a pendulum, right? And review what the potential energy of a pendulum was in a gravitational field. Okay, if you remember, the expression for the potential energy of a pendulum was found by kind of taking the height from the bottom, and it was equal to mgl times cosine theta. Well, it turns out in this case, when is the potential energy of the dipole the largest? It's largest when the positive part is pointing against the field and the negative part is pointing with the field. That's going to cause a slight perturbation, is going to cause that thing to swing back and forth and back and forth. So instead of gravitational force and length of the pendulum, we now have strength of the electric field and magnitude of the dipole moment. And so that's where we get this equation of P times E cosine theta. It's also often written as, or cosine phi. The book uses cosine phi. Another way to express it would be the dot product of the dipole moment with the electric field. So what does that mean? That means that the dipole has the lowest potential energy when the positive charge is pointing with the field and the negative charge is pointing against the field. That would be the equivalent of a pendulum just hanging straight down. That's when the potential energy is 0. You can't, the electric force won't do any work to cause it to increase. And so you see the graph right here, right? The graph is what you would expect to see for the potential energy if it's a function of cosine. So that was a brief intro to potential energy. And in the next video, what we'll do is we'll talk more in detail about the more fundamental concept, which is called electric potential. They're different quantities, and they're also related. So until then, thanks for your time.